Okay, so last class we started looking at phase noise in VCOs. Let's do a quick review of what we did last class. So we started looking at the exact definition of phase noise, what it would probably look like in an oscillator, and we said very close to the oscillator the phase noise would increase, and far away from the oscillator the phase noise would decrease for various reasons, right? And we said, okay, so if it was just pure up conversion as a mixer, it would look like from the bias noise, you will have a 1 over F and then maybe thermal noise, right? As we are going to see in today's class, that is not exactly the way the oscillator noise looks like. And we said this is really noise in the phase of the oscillator, and there is nothing to actually reset the phase of the oscillator once it has changed due to noise, right? So really the phase of a free running oscillator is undefined. There is nothing to control it, and more or less the ideal oscillator should have a constantly increasing phase. But if you take an oscillator with noise, you will get some variation around this due to phase noise. The definition of phase noise is 10 log of the ratio of powers of the power in a 1 Hertz bandwidth of noise to the overall signal power. Okay, the overall signal power is pretty straightforward. It will just be the depend on the amplitude of the sinusoid at the output. Okay, we also looked at some effects of phase noise. For example, if you are in a receiver, you are trying to receive in the presence of a large interferer. If phase noise is large enough, it could actually completely drown out the desired signal. There are other cases where it's obviously a problem. If you have a very large high power transmitter and with LO phase noise inside the transmitter, then you will not be transmitting power only at the desired frequency. You will be transmitting power at other frequencies also. And finally, if you are doing some kind of OFDM modulation, you wanted no intercarrier interference between the subcarriers. But if you have phase noise for each of those subcarriers when you are trying to generate them, that would also be a problem. So there are various places where phase noise is a big problem, and so you need to, when you design the VCO, understanding phase noise and understanding how it comes about, as well as understanding how to improve the phase noise performance of the VCO is extremely critical. And really we are going to look at two different representations of phase noise. The first one is an LTI representation where you try to analyze the oscillator as a linear time invariant system, try to find out how noise actually ends up at the output. This is not a true complete picture, because we know that first of all the oscillator is nonlinear. Second of all, as we'll mention in next class, as far as noise is concerned, the oscillator is a time variant system. We'll see why it is a time variant system next class. But having said all of that, the LTI analysis does have a couple of major strengths. The first one, obviously we are all comfortable with LTI analysis. It's much simpler. The second thing is, it does give you a lot of insight into what you expect to happen when certain things are changed in the system. It may not give you an exact representation of the complete noise of the circuit, but if you do certain things, if I double the current, what should happen to the noise in the oscillator? If I double the amplitude, right? Or if I change the Q of the resonator, how does the phase noise change? If I change the frequency of operation, if all I do, I keep everything else the same, but I double the frequency of the oscillator, what do you expect the phase noise to do? All of these things are fairly well explained by the LTI analysis itself. So we will understand that first. Next class we'll look at the time variant analysis. This is the original reference for the LTI analysis. Obviously people have adapted it to modern, more modern types of presentations, but this is really where it all comes from, right? So we said actually before we even draw this network, you should understand what the Leeson's model says. Okay, so first of all, Leeson's model says the following, or rather it explains the following. If you take an oscillator and measure the phase noise, you will find this. Okay, I'm just going to draw the single-ended side. around the, I'm going to plot the phase noise as a function of delta f. Okay. So if you actually take an oscillator, build an oscillator and measure the phase noise, you will find that the phase noise has three distinct regions. Okay. In fact, I'll draw it a little bit better. This way and this way. Okay. The phase noise has three distinct regions. Okay. In region 1, very close to the oscillator, the phase noise as a function of delta f has a 1 over delta f cubed kind of behavior. In other words, it goes at around minus 30 dB per decade. Okay, you're talking about the ratio of power. So it goes at minus 30 dB per decade. In this region, okay, the second region, you move a little bit further out, it goes at 1 over delta f squared, okay, or minus 20 dB per decade. And then you finally hit a region where the phase noise, it looks like broadband thermal noise. Okay, so if you take almost any oscillator and look at the right set of frequency ranges, you will see this kind of spectrum. Okay. Obviously now you go back and look at a very simplistic mixer type of analysis. It doesn't seem appropriate for this, or rather it doesn't seem like that is all that is happening. There seems to be something else that is happening, because if you just look at what we drew last class, okay, we said, okay, the noise in this gets upconverted. If that were all that was happening, you would only see a 1 over f and thermal. But now we are actually seeing a 1 over f cubed, a 1 over f squared region and a flat noise region. So there is something else that is happening. So we need to be able to explain each one of these regions. Obviously the way you know your theory is complete is when you can actually predict each one of these regions. And not only predict the noise levels, but also predict the transition points. Right? You need to be able to do all of these if you have a complete theory. If you look at Leeson's noise model, what he does, or what the theory does, what the LTI noise theory does, is it explains or rather it empirically postulates the presence of each one of these for any oscillator, and it uses an empirical factor to try to account for some of the noise increases from what you would normally measure. So you are, based on LTI analysis, you may get a certain level, but if suddenly you notice that noise is 5 dB higher, you can postulate the presence of some unknown factor S, right, which actually compensates or accounts for this extra increase. Now it is not so obvious what this empirical factor is or should be. It definitely does not help predict the noise. It only helps try to explain it in a roundabout manner. Okay, but it still has other strengths, so that is why we will still go ahead and learn it. Okay, of course these are all in log scale as I have drawn it. Okay, so we started off with this model, so I'll just copy it again. Okay, we started off with this model of the oscillator, where you have the RLC tank. Okay, you have a noiseless energy transfer system, a noiseless energy restorer, if you want to call it that way, and you have the noise from either of these systems being represented by a current noise. Okay, now the first thing you have to remember is we are really interested in the phase noise of the system. Okay. What we are going to do is, as we have always done before, we will analyze the overall noise at the output. Okay. There is a certain assumption we'll make. The assumption we'll make is that any noise in the, let's say, the voltage across it is equally distributed between the amplitude of the noise and the phase of the noise. This is normally true because noise being a random process, you would expect that equal powers are distributed in all degrees of freedom possible. In this particular case, the degrees of freedom possible for the for any any particular signal, you look at it in the frequency domain, the degrees of freedom possible are in the amplitude and the phase. We will assume that it's equally distributed in the amplitude and the phase, which is not an unreasonable assumption. Okay? So we will analyze the overall noise power across these two nodes, take half of that and attribute that to the phase of the signal. Phase of the noise. That seems like a straightforward assumption, yes? Correct. Yes. Even here, what we'll do is, we are going to find out the output voltage. Okay. Rather, we are going to find out the output noise power in the voltage across these two nodes. Because when you actually tap off this signal, you are going to tap off the voltage. Okay. If you want to be dimensionally correct, you will take, let us say, half this power is in the phase of the noise. It's okay, perfectly okay to just take the noise power, take it down by half, because the way phase noise is defined, you are actually defining it with respect to the signal power. Okay, so there is really no problem with dimensionality as such. Okay, as long as you take noise power and compare it to signal power, you are doing perfectly okay. If you are actually talking about the actual noise in the phase in terms of voltage or in terms of, if you are talking about amplitude, you'll be talking about in terms of voltage. In the phase, you might be talking about radians, right? If you are taking it in that form, it becomes a lot more difficult to actually try to compare it to the signal power, right? You could still do that. Absolutely, that's right. Okay, so that is why it is just very convenient to use this in terms of signal power and noise power. We'll just go ahead with that.
You talked about so one more way to stress this is something like the sine component and cosine component.
Which is equivalent to the amplitude and phase, but if you split it into the sine and cosine, then what you should do is you should split the signal into the sine and cosine components if you knew the exact phase of the signal. So in other words, what you're saying is, if the signal really had an in phase and quadrature component, you would split the noise also into the in phase and quadrature component and find out the individual noise to signal ratios. Right? That is what you will have to do. But in reality, this is much more convenient and much more relevant for an LO signal, because you are really interested in the zero crossings and you are interested in the phase. Okay, correct. Yes. Yes. Correct. That's right. Okay. So we are going to represent all these noises as one single, IN squared by delta F.
Actually, it doesn't matter how you split the noise, because you are just interested in the signal power.
No.
The noise power.
No, that is absolutely right. The noise will split equally either way. That is not the problem. We need to see what we are interested in. In this particular case, we are interested in the zero crossings, the change in the delta T of the zero crossings. Therefore, we are interested in the phase. Okay, so that is why, of course, you are right. It will not matter as long as it splits equally. It will not matter. Okay, so we are going to find out this, the frequency response of the tank. Okay, and then we are going to apply this noise current source, equivalent noise current source, multiply it with the frequency response of the tank. That will give you the output voltage. That seems like the best way to analyze this in an LTI way, and that also happens to be very straightforward. The only difference is, if you want to actually represent it in this form, where phase noise as a function of frequency offset, then what you need to do is, you don't just have to get the frequency response of the tank as a function of frequency. You want to get it as a function of the offset frequency of delta F. Okay, so that is what we are going to do. So we'll say say, let's say delta omega. Okay, it's easier to obviously analyze without all the 2 pi factors. So we'll say at a small frequency offset delta omega, we are going to find out y of omega naught plus delta omega. Okay, we are going to represent that in terms of obviously the real part and imaginary part. So you'll have some g plus, this is for the tank, for the LC tank. So we have y of the omega naught plus delta omega. You will have the r 1 over r, which will be g, plus j of omega naught plus delta omega times c, plus 1 over j of omega naught plus delta omega times L. Okay. So now we will have to simplify this in some manner. So so this is jg into omega naught plus delta omega times L minus omega naught plus delta omega whole squared times LC plus 1 over j omega naught plus delta omega times L. Okay. The reason we are doing this is, of course, to find the expression as a function of delta omega, and we also know certain identities. Obviously, the assumption is omega square LC is 1, right? That is something else we can use. Okay. So if you actually simplify this a little bit further, of course we need not have taken probably g inside the fraction, but you will get g plus j 2 omega naught delta omega over omega naught plus delta omega times c. Okay. As it so happens, the L factor gets cancelled. Okay. And it's a function of g plus this, right? G plus 2 omega naught delta omega by omega naught plus delta omega times c. Which means if you want to find out the impedance of the tank, okay, you have to take 1 over this number, so you will get some expression which looks like this. It's 1 over g times 1 by 1 plus j2 omega naught delta omega by omega naught plus delta omega times RC. Okay. Now we are going to try to not just simplify this further, but rewrite this in a slightly different form in terms of quantities that we already know about the RLC tank. Obviously, one thing we used was omega naught LC is 1, omega naught square LC is 1. The other thing we are going to use is the representation of the quality factor of the tank. Okay. The reason is this. We know that as the quality factor of the tank increases, the filtering ability of the tank for noise also increases. Therefore, the phase noise should get better and better, right? So we want to give this representation inside the expression for noise itself. So we know that Q is omega naught RC. Okay, so we can rewrite the impedance as R times 1 over G is nothing but R, 1 by 1 plus 2Q J delta omega by omega naught. Okay. This is just a simplified representation of what we have so far. Now we need to find out the magnitude of the impedance. Okay. Then multiply the current noise by the magnitude of the impedance squared to give us the voltage squared number. So the magnitude is r omega naught over 2q delta omega. Okay, and if you look at Vn squared over delta f, okay. Now I have made one approximation here when I move from here to there. The approximation is that the Q is sufficiently large. Okay, only then the magnitude can be written in this single form. Okay, the Q is can be sufficiently large and you'll be fine. So Vn squared by delta f should be In squared by delta f, okay, times mod z squared. So I can write it as 4 kT times G times R squared. What is this 4 kT G? This is the noise due to the resistance of the RLC tank. So in fact right now I am even assuming that the noise restorer of the active portion has no noise. Let us start off with that, because this is really the easiest way to start off your analysis. Okay, so I am going to represent the total noise itself as 4 kT G, okay, times R squared times omega naught squared by 2q delta omega the whole squared. This is 4 kT R times omega naught by 2q delta omega the whole squared. Okay. Now of course half of this should appear as phase noise. Okay. Now, so half of this appears as phase noise, and then now we also know the noise power, so we can compare it to the signal power and go ahead and find out the actual expression for the phase noise itself. So the phase component is 2 kTr omega naught by 2q delta omega the whole squared. So now I can write it as L of delta omega, which is a phase noise at an angular delta omega offset, is 10 log to base 10 of 2 kTr okay, this expression by, what do I put here in the denominator? The power of the signal. So I am using voltage squared quantity for the noise. All I have to do is find out the output amplitude, take the square of that, and that will give me my signal power in voltage squared terms. Okay, I'll just call that Vs squared. Okay, depending on the particular amplitude you have, this will change, right? But this is your number. So I'll rewrite this 10 log 10 Vs squared by R. I'll write it as I'll call it the signal power. The impedance is R, the Vs is the output amplitude. So I'll kind of call this I'll kind of call this as some P sig. But really it is just a different way of writing it. Okay, so just remember that. PS or P sig is okay. By 2q delta omega the whole square. Okay, so this is the expression that we have come up with for phase noise. So first of all, if we try to plot this, what does it tell us? Let's say I try to plot this as a function of delta omega on a log-log plot. What kind of plot will you get with this equation? Minus 20 dB per decade. Okay, so you get something like this. Okay, you will get a minus 20 dB per decade phase noise. Now this is actually a good thing, right? Because it seems like you have found one explanation for the 20 dB per decade region. Okay, so it seems like a majority of the noise in the 1 over f squared region of the VCO phase noise comes from thermal noise, which is being filtered by the tank by the frequency dependent response of the tank to give you a 1 over f squared kind of behavior. In other words, you get a minus 20 dB per decade kind of behavior. Okay? You will still see this. Okay? You will still see this, which is why this LTI analysis is not complete. Okay? It seems to explain things in some manner for harmonic oscillators, for LC resonator based oscillators, but not necessarily for other kinds, ring oscillators and relaxation oscillators and so on. All of, even a ring oscillator will have a 1 over f cubed region, 1 over f squared region and a flat noise region. Okay? And the linear time variant analysis actually explains everything. Okay? So, the 1 over f squared region seems straightforward. What about the 1 over f cubed region? How do you think you would explain that? Correct. If you inject flicker noise where you are injecting thermal noise, you would get the 1 over delta f cubed will come from 1 over delta f squared will come from the frequency response of the tank. The other 1 over delta f should come from the behavior of the noise itself to give you a 1 over delta f cubed region. So, okay, or rather what we should say is may come from. May come from may come from 1 over f noise filtered by the tank. Okay, so now if this is the case, okay, so I should underline this may come from. The reason is this. Now we need to look at this a little bit closely. We are saying 1 over f noise can maybe filtered by the tank to give you 1 over f cubed. In which region do you see 1 over f noise for a transistor? At very low frequencies. If I take a transistor, I'll probably see 1 over f noise, for a few tens or up to maybe if you take a very low transistor with a very small length, you may see it up to maybe several tens of megahertz, maybe even hundreds of megahertz. But if I build an oscillator at 4 gigahertz, I should see very little contribution from 1 over f noise, because what we are talking about is the frequency response of the tank at omega naught. Remember, right? This is not just at any frequency. We are talking about the frequency response of the tank around omega naught. If I build a 4 gigahertz oscillator, but I have flicker noise only up till 100 megahertz, right? Does it mean that I would never see noise, I would never see a 1 over f cubed region? Correct. So one thing which is definitely possible, initially we thought, okay, there is some mixing action, right? And that noise gets upconverted to 1 over f noise. But we don't see a 1 over f kind of behavior anyways at the output voltage. We did the LTI analysis. We found out that the frequency response of the tank is 1 over f squared. But directly multiplying the 1 over f noise with this, that should not happen. However, one possible phenomenon is because of the cross-coupled behavior of the cross-coupled pair. If I have 1 over f noise here in the bias proportion, that should get upconverted by the switching pair, because the switching pair is switching at f naught. Okay, so if I look at the effective noise here, that actually looks like the 1 over f noise is upconverted around f naught. Okay, so remember, if I have around DC here, okay, if I look at this point, I should actually see, something like this. Okay, so definitely that is one possible explanation for the existence of the 1 over f cubed region. First, the bias noise gets upconverted by the switching pair, then it gets multiplied by the frequency response of the tank to give you the 1 over f cubed region. Okay, let us suppose that this is one possible mechanism. Then the next question which remains to be answered is this. Let us go back to the plot that we drew. If this were the only case, let's call this, these two corners as 1 over f cubed, f1 over f cubed and f1 over f squared. This is the transition between the 1 over f cubed to 1 over f squared region and the transition from the 1 over f squared region to the flat region. If it is purely coming from the bias, what should this be equal to? What should the 1 over f cubed, f1 over f cubed, what should that be equal to? Okay, even if there is thermal noise, yes, correct. Then it will be different. So let us also put that down. Okay, we need to know is 1 over f cubed equal to 1 over f corner of the bias device. Okay, if not, okay, is this explained just by additional thermal noise from the resistor as he said? Additional okay. There is a third question, right? What is the third question? So we have looked at this 1 over f noise. Is it the same as the 1 over f noise? 1 over f cube corner is the same as the 1 over f corner. If not, is this the same as the? Is it only due to the change in noise level? Because the noise corner will be different if you add extra thermal noise. Is the bias device the only device inside the circuit? You also have the cross-coupled pair. Does the 1 over f noise of the cross-coupled pair make its way to the output? We have not explained that, right? Okay, yes. Mm-hmm. Mm-hmm. Exactly, good question. We are going to come to that next, right? We have taken up this expression, okay, when we calculated the impedance, okay, we have taken up the expression, but we have not taken into account this minus RA, right? What do you do about the minus RA? Any ideas? We wrote the expression as if minus RA didn't exist at all. RA is smaller than R. Okay, so does that mean there is a residual negative resistance then? That makes it very dangerous, right? So what do? Actually, what is the problem here? So let us assume that there is a negative resistance minus RA. We are analyzing the noise in steady state. Okay, so R should be equal to minus RA. Correct? Does that mean this is an ideal LC tank? So there should be no noise at all, right? No, correct. So the power domain, the noises will add, but once you have a minus RA in parallel with R, the two cancel out, giving you an ideal LC tank. Whatever noise you have outside, if you try to put it through an ideal LC tank, it will only give you a pure oscillation without any noise at all, right? what is the fallacy here? Obviously there has to be a fallacy because this seems too good to be true, right? So what is the problem? No, of course it does. You know that the negative resistance has some noise contribution. But it actually, see, first of all, it does not matter whether it has contribution or not. What I am trying to say is, the negative resistance portion, the active portion gives you minus RA. In steady state, that minus RA should, the magnitude of that RA should be exactly be equal to the parallel resistance of the tank. That's what we've been saying so far, right? Once that happens, if you look at this system, it looks like an ideal LC tank. Okay? If you try to inject some noise into an ideal LC tank, what happens? Doesn't matter whether it's broadband, it's frequency dependent noise, white noise, colored noise, doesn't matter. Right? The LC tank is ideal. It will choose only the noise component at omega naught and nowhere else. If you actually try to look at this, look at the noise outside, it will look like there is no noise. Right? It will look like an ideal LC oscillator. Okay, so what kind of frequency dependence does it have? That is right. So actually what happens is, if you look at this negative resistance, first of all, it's not a linear resistor. Okay, what we have been saying is, due to the behavior of the circuit, during different portions the transistors go through multiple regions. What you know is that at the end of one period, you have actually restored whatever noise, whatever energy was lost in the resistor. Okay, this is not a linear small signal resistor. Similarly, the noise restoration, the energy restoration happens only at omega naught to give you the fundamental oscillation. If you try to go a little bit away from omega naught, this energy restoration is not perfect. Remember, because the way we have been looking at this minus RA, we have been assuming at omega naught, the transistor switch at omega naught, we have been assuming it's minus 2 over GM, right? That is not necessarily true. That is true, the transistor switch and the periods will be exactly equal only at omega naught. If you try to move a little bit away, there will always be a residual resistive component, and therefore the actual frequency response of even the energy restored tank will have some, resistance, some losses at other frequencies, and therefore it won't look like an ideal LC tank. It will look like a real LC tank, but the closer and closer you get to the fundamental oscillation frequency, the better and better it will look. It will look closer and closer to an ideal LC tank. So in other words, you really need to take the equivalent resistance between R and minus RA. This will have a residual positive component at all other frequencies other than omega naught. At omega naught, it will be 0. Yes.
Can you also look at this R?
Hmm. Correct. Okay, series resistance of inductor and capacitor. Correct.
So the transformation from series to parallel is very only a single frequency.
It is not. Okay, so it is. Okay. It is valid over a narrow band of frequency. It is exactly valid only at a single frequency. Correct. You can think of it as another reason why this may be different. However, suppose I took an ideal, LC and put a resistor across it and then try to analyze it, try to build an oscillator. Okay, mathematically this is very easy to try out in simulation. You take an ideal inductor, ideal capacitor, ideal resistor. Instead of building your RLC tank as L in series with R and some capacitance series with R, if you in your simulator or in your analysis, if you actually build the tank like this, you will still see a problem when you move away. So that is not the fundamental reason. Okay, that may be an additional reason why the frequency response differs from what we expect it to. Okay? Yes, it is possible. In fact, so if you actually take up, I was actually coming to that next, if you actually take up the real analysis, in fact, it is not just optimistic. you can see, let us look at where all we have used G, right? Instead of using G, we'll have to use G equivalent, right? Some G equivalent, which is the parallel combination. Okay? Sorry, where is the correct? Okay? So we have used G here. Okay? When we go down here, we have actually used G and R here. The really big point where it will actually impact you is in the expression of the Q. Okay? So what you have assumed is this Q is the unrestored, unloaded Q of the tank. Okay? In reality, the Q you have to use is the Q of the tank in addition with the energy restorer. And that Q will be a function of this delta F. You understand? So, in reality, it is actually very pessimistic. Okay, it's not optimistic, it's pessimistic. Okay, that is why even when you take tanks with very low Qs, okay, Qs of 4 or 5, you can still build relatively low noise oscillators. Okay, it is not just, if you build tanks with, Q of 4 or 5, the bandwidth seems like it is pretty large, right? The actual Q you would expect, so let us say at 2 gigahertz, you build a Q of 5. What should the bandwidth of the tank be? The 3 dB bandwidth of the LC tank, what should it be? I have at 2 gigahertz, I am building with a tank of Q5. What should that two-sided bandwidth be? 2 by 5, 2000 by 5, which is 400 megahertz. Okay. The offsets we are talking about, okay, are of the order of kilohertz and megahertz. Right? If you really think you are going to analyze it as a function of Q, it seems like the tank has practically no frequency response. For, it has only 3 dB loss or 3 dB shaping over 400 megahertz, plus or minus 200 megahertz. But these offsets we are talking about, if you take an oscillator, the 1 over f cube corner could be maybe a few tens or hundreds of kilohertz. Okay, the 1 over f squared corner could be of the order of several megahertz. Right? That itself shows you that you cannot just pick up the Q of the raw Q of the tank. You will have to use the modified Q. Okay. So what I'll do is I'll put up the analysis for the modified Q also, but it's, you probably don't need it. Because you can do it yourself, right? It's very straightforward. You'll just have to assume that apart from this R, you also have an minus RA, and it has an effective positive component. So the effective Q of the tank is actually much higher than the Qs of the RLC tanks that you start off with. Okay, that is the really important point you need to take away from here, as far as noise is concerned. Okay, so this is, we have come up with some kind of expression. Now we need to move from this LTI expression to Leeson's model. Okay, Leeson's model really is just this kind of LTI expression, but tacking on tagging a couple of empirical factors and things to compensate for the 1 over f cubed region. So let us just write out Leeson's model. Or Leeson's expression says this phase noise L of delta omega should be 10 log 10 2 kT by P sig was our original expression. I am going to tack on an extra factor called F. Okay. Now I need to get the 1 over f cubed, 1 over f squared and the other flat noise region. So the expression which we had as just the 1 over f squared noise is going to be replaced slightly differently. 1 plus okay, so So really this expression says the noise is 10 log of 2 kT by P sig times some factor f times you now have two terms. You have the first term which is 1 plus omega naught by 2ql delta omega the whole square times the second term which is 1 plus delta omega 1 over f cubed by delta omega. Okay. Now obviously now you must have several questions. What are the different questions you have about this expression? Okay, now let us assume you know the first portion what we did so far in class and you know Leeson's model now. Okay. What do you understand from this expression and comparing it to the previous one? Correct. So at very low delta omegas, what happens? You expect these two terms to dominate over that one. Okay. So you will get a 1 over delta omega cube term. Okay. So it actually, the good things about this, 1 over f cubed region is represented. Right? What else? 1 by q squared term. Exists. Obviously the power of the Leeson's model also exists because if I actually take an oscillator, I take an oscillator that I've built with a resonator, okay, and I'm going to double the Q of the resonator. So I initially start off the resonator of Q5, I'm going to double the Q to 10. What should happen to the phase noise of the oscillator? Okay, now we know that this is not really Q but QL, that's why I wrote it as QL, which is the loaded Q. So first of all, this loaded Q, this term itself is loaded because you have, when people normally say loaded Q, they refer to the fact that if you just take a resonator, okay, it may have some Q by itself, which may be 5 or 6 or 10. If your circuit that you're attaching to this resonator has an input resistance, that will also change the overall Q of the frequency behavior. Okay, if you actually look at the overall frequency behavior, it will not truly represent just the frequency behavior of the tank, but it will include that plus whatever loading happens because of the circuit you are connecting to this. Okay, so now this can mean two things. One, if you just take a VCO and try to connect something to it directly which has some input resistance, obviously several things are going to happen. You know that for example, the amplitude of the oscillator depends on the parallel resistance of the tank. We know this. If you take a circuit which has an input resistance which is going to appear in parallel with this, the amplitude will immediately fall. Right? Okay. Number two, apart from the amplitude falling, you know that the frequency response to the tank is going to change, so the noise response of the oscillator is also going to change. Okay, so you know both of these things. However, we also know that when we say Q here, we don't necessarily mean just the Q of the tank or just the linear Q. We are also talking about the fact that this Q itself is a function of frequency of this delta omega, not just a function of frequency, but a function of delta omega. Okay, but definitely this Q behavior with delta omega is a strong function of the initial Q you start off with, because you start off with an initial Q. To compensate for the losses due to that Q, you try to build an active resonator. So they will be strongly correlated. Okay, so we can tell that if you start off with an initial Q of 5 and I increase that Q to 10, what should happen to the phase noise? It goes as 1 over Q squared. Okay, so at least in the 1 over F squared region where this term is dominant, okay, you should see that if I just double the Q, what should happen to the phase noise? Yeah, so how much is that? 12 dB. Okay, so the phase noise, if I just take the exact same circuit but double the Q, the phase noise should get better by 12 dB. Okay, and this theory actually, or at least this expression, definitely explains that. Similar to our original LTI expression. What else? Yeah, so these two things are very good. Okay, does it explain dependence on omega naught? Yes, it does. Okay. So what that means is I take a 2 gigahertz oscillator, I measure the phase noise behavior. I build a 4 gigahertz oscillator. What do I expect? Fundamentally, I expect the phase noise to be worse for the 4 gigahertz oscillator. So fundamentally, it's going to be tougher and tougher to build oscillators at higher frequencies with the same noise behavior. Okay, that is what this also says. Now, apart from that, there are a number of, I wouldn't call them deficiencies, so maybe I shouldn't use a minus sign but an arrow sign. There is an empirical factor F. Okay, because what happened is you take what happens is you take this LTI model that we have developed, you try to build an oscillator based on that. Suddenly you find that the oscillator has 6 dB more noise. Okay, 6 dB is a lot, right? It means the noise power is twice. What could be the reason for that? Let's say we don't know, but let us say we build multiple oscillators. We find that this difference is approximately 5 to 7 dB. You will be tempted to put in a factor of 2 inside the expression and say somehow there is something which doubles the noise, but we don't know what that is. I'm just giving an example of double, but it could be other numbers also, right? Now, unfortunately, this empirical factor F, if you really want to be accurate, it is very dependent on the type of oscillator that you build. Okay, so really, I mean, what we are saying is we don't know what's going on, but we are going to plug in some factor to make it work.